Hi, good morning. I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program. As I talked before, I've been very fortunate to conduct what I call these systems conversations with wonderful speakers that we bring to Cornell. And today I'm really delighted to introduce to you Dr. Michael Watson. Michael, he's currently the Deputy System Engineering and Integration Lead for Human Learning Systems at Dynetics. And also, actually, before that, Michael has led the NASA System Engineering Research Consortium, defining advanced systems engineering approaches and also the basis. I think this is really very fundamental. Michael, thank you for doing all the work. I know that system engineering, the name has been out, but I feel it's still an emerging, powerful area. So I was looking at your research and also your career, and I believe all of us would love to learn more about how your career, how your interest and your work in system engineering evolved throughout the decades.
Oh, sure.
Yes.
Sure, yeah. So I've always had a systems interest in looking at the whole system, not just a piece of the system or a portion, but how the whole system functions together. So that's always been my interest. I came into NASA in 1989 in operations, looking at Space Station and Space Lab. And about 3 months in, I was asked to take on a project to lead the definition of the payload training complex. And that really fed my systems interest. I became what today we would call a lead systems engineer for that project. And that involved simulation of the entire space station in order to train the crew in how to operate the payload. So it involved simulations of all the systems for space station, including the structural components as well as the data systems and thermal and life support and communications and putting all the pieces together. That was really fascinating to me, and I really spent a lot of time doing systems engineering, writing requirements, working across interfaces, doing all the pieces that you would see in systems engineering. I moved over after that, went through preliminary design review. We actually transitioned that program to be part of the Space Station Training Facility, which exists at the Johnson Space Center today. And that was really to help with crew travel and not to have the crew be apart from their homes while they were doing extensive training, getting ready to then go on orbit for several months from space station. So that gets into the social side of things and how that impacts people and their lives, in this case the flight crew, their lives and their families, and learning how to deal with that. And so it made sense, actually, to make that transition. I moved over to be the Payload Data Services System. I was actually to take that project on from its definition phases and led that through its PDR, and was really interested to look at how we are transmitting data across the world to different principal investigators and to enable that, right? So today, all of the payload data that comes down from space station and video, it goes through the Payload Data Services System, which has gone through a couple of different forms since we initially built it. It's very software-centered now, whereas when we started, there were a lot of hardware pieces to it, hardware data processors. And so it was very, very fascinating to look at that. I moved on from there, got my master's and my PhD are in electrical engineering from the University of Alabama in Huntsville. I should say my bachelor's is also in electrical engineering from the University of Kentucky. And when I went to UAH, although it's a double E degree, it's in optics, right? And optics has a very broad system focus because there are a lot of things about the other aspects of the system that affect the optics. Vibration, thermal, mechanical alignment, all of that plays into the optical systems. So again, that kind of fed my systems focus. I managed our optics branch for a couple of years, looking at optical system fabrication, which is really interesting. Then I moved over and began working in what's called system health management. And to do system health management properly, you have to have the full system perspective. You become very aware of the coupling between different components of the system and the interactions that happen in the different aspects of the system and how they work together. Because what we did with that is first of all, led an activity defining vehicle management systems for missions to Mars. And we actually presented that to the National Academy of Engineering as part of a larger study. And that was really interesting to look at and kind of get definitions of what it means to have that total system perspective and how to manage the whole vehicle, not pieces of it. And what you find is that the couplings are really the important management parts. A good friend of mine, Stephen Johnson, really pointed that out to me early on as we were concluding the work on that study. It's systems engineers, as Stephen would say, own the interactions between the systems, but not really the pieces themselves, right? Mm-hmm. Mechanical engineers own the mechanical pieces, electrical engineer own the electrical pieces, software engineers own the software pieces. But where those come together and interact, that's the domain of the system engineer. And so we really kind of developing that as we went through Constellation. I formed the health management branch at NASA in 2004. I was asked to do that by the department manager at that time. And we took the vehicle management system model, and we said, what does this look like for launch vehicles? And from that led the abort work that we did for the Ares 1 vehicle in the Constellation program, which is still part of the Orion vehicle, the early interfaces that we did there and how they trigger aborts. That concept is what is in the design today. And so we developed a lot of that work for the Ares 1 vehicle. That led in, after that program was canceled, we looked to stand up then the Space Launch System, and part of my career was actually involved in doing that. I was part of the original program formulation team and how to bring that program together. I led or facilitated the rack analysis cycle that we did to really study the different configurations for the Space Launch System. And so what you see out at Kennedy Space Center today on the pad getting ready to launch is what we decided the configuration would be in that study back in 2011. And so I got to stand that up. In the aspect or in the process of doing that, I also had an opportunity to meet with former NASA Administrator Mike Griffin, and we talked about what is the basis of systems engineering? How does what do you do that makes a system successful? And we recognize that you can follow process, and NASA has a really well-documented systems engineering process in their handbook. You can follow that process, and you can be really successful. But you can also follow that process and never have the system come about, have a complete disaster. And so we recognized that it really wasn't the execution of the process that was making systems successful. So what is it? So we went off and formed a Systems Engineering Research Consortium, which you can access the results of that online now. And at www.nasa.gov/consortium, for those that would like to Google that. And what we found is that systems engineering really has two basic bases. One is the physics of the system itself. There are actually physical bases that are cross-cutting and integrate all the interactions of the system. We also found that there is a big social basis in systems engineering. Sociology is important because systems engineering works across multiple disciplines. And you can look at each discipline as having its own culture that's been defined over thousands of years of development within those cultures. So mechanical engineering has a culture that's taught through all the universities and schools, that's been developed over hundreds, really thousands of years in execution of mechanical engineering aspects. You can go back to the works of Vitruvius, for example, and see some early definitions of mechanical engineering, of civil engineering. You can go back. Electrical engineering is really defined by the works of Maxwell, and how that gets pulled in and put together. And you're not going to change those cultural understandings, even when they overlap, of what they are. Systems engineers then have to work across those many subcultures and bring together a solution that makes the system work. So sociology became really a really important focus in that. And so we realized that there's really two focuses to systems engineering in our consortium work. One based on the physics, or if you're looking at data or communication systems or cyber systems, the logic that's in place there, and the other being the social. Mm-hmm. And so we studied that quite a bit, the consortium that involved 17 different universities, a couple of NASA centers, Air Force research labs participated in it, and we learned a lot about systems engineering. And one of the things that came out of that was the systems engineering principles that ICOSE just published 2 months ago, back on August 19th. And those principles really show you both the physics side and the social side of systems engineering, and how they're related and how they affect everything that a systems engineer really needs to do. And what they do is they provide guidance in the application of the systems engineering processes. It's interesting, if you really go and look at the different engineering disciplines, they all have processes, but they really don't describe themselves by their processes. They describe themselves by other attributes that they are producing using those processes. And that's what we were trying to get to with systems engineering. What do those attributes look like? And the principles are a first step. They're not the final step. They're the first step in how we get to that. And one of the principles, the 15th principle from the ICOSE viewpoint, defines the basis of systems engineering as a systems theory basis, a physics and logics basis, a sociological basis, and a mathematical basis. And mathematics was really came about through our AFRL collaboration, and they were working with a mathematical category theorist who had looked through the NASA systems engineering postulates, which became part of the systems engineering principles when you look at the ICOSE work. And he said, well, you realize that your second postulate is the definition of a mathematical category. And I wasn't familiar with category. I said, no, I didn't know that. And what we realized in working with Larry Lamb, who has now passed away, unfortunately, that the postulate that we had put out there is actually the mathematical basis of systems engineering. That is category theory. And category theory, Saunders McLean kind of developed that and published that in a paper in the early 40s. His book is still the best book to look at for that. But it hasn't really been well studied or applied to systems engineering. It's basically been studied as a set of mathematical axioms. Well, what we're doing now is we're looking at that and saying, these axioms really define what a system is and what a system structure is. I believe that the axioms of category theory are an important part of model-based systems engineering. And once those are more explicitly connected, I think we will see great progress and advancement in the discipline of systems engineering. I believe that mathematical structure allows us to move beyond what we currently understand. And you see that in the other engineering disciplines, right? You saw civil engineering practice for 6,000 years. And all of a sudden, Galileo came up with strength of materials. And we went from basic structures that we knew how to build that you can see in the Roman aqueducts and the great cathedrals in Europe and those large buildings that they produced, but nobody could ever move past that, right? From the time of the Romans to the time of Galileo, nobody ever moved past it. And then the strength of materials law was produced by Galileo, corrected one of the constants. And then we started seeing, and Henry Petrosky in his books, Henry's with Duke University, his books really kind of lays this out. You can see the advancement of that engineering understanding really leading to the Golden Gate Bridge, the large suspension bridges, all the massive, very intricate bridge structures that we see today came out of the work of Galileo that allowed us to go beyond what we had learned in practice to new avenues that we were not finding by just trial and error by itself. It's began to give us a guide in how to move forward. That's what we're seeing with systems engineering. That's where we think category theory will take systems engineering, is it's going to give the basic guides of what really works, what doesn't, and how to move that forward. And so we see that as a real advancement for the discipline of systems engineering, and that advancement is just now emerging, right?
Yes, Michael, that's wonderful. You brought out this mathematical theory, category theory, and also you point out the hope. Yeah. And I think actually that is something I believe in the system engineering field has been struggling for a long time. Right, but I think I really like the analogy that you made with, for example, civil engineering and even mechanical engineering. Right, it's really like, as you say, Galileo, and then when they invented find approach to characterize the materials using kind of the strength, material strength, and then move that on, and then all the way to the design. Of course, nowadays finite element method, computational method, such that all these previous science almost becomes a commodity, yes, like a computerized. So, but I think for system engineering, as you mentioned, it's really about the interfaces, the coupling, and the interaction. So, Michael, I think for many general public, yes, they have heard about system engineering a lot, and they're probably they've been asking, okay, what system engineering is really about? And I feel there is probably no better place than NASA to really exemplify, what system engineering is about and the power of system engineering. Can you I think it's big because I believe that NASA played a very key role, and for example, your team, your consortium, that played such an important role in helping. Of course, now you're talking about system engineering as a discipline, but before, and as you said, like system engineering, 6,000 years, it's just practice. Right. And I think you're absolutely right. And my observation is that you can see NASA and all, Lockheed Martin, Boeing, BAE Systems, and MITRE, all these organizations and industry sectors, they realized the power, the need of system engineering long time ago, but it seemed like the advancement of system engineering as a discipline has been falling behind, right? Yes. It has been trying to catch up. So now at NASA, so can you imagine? Can you give us more example of like the power, the necessity of system engineering at organizations like NASA? And imagine that if you had not practiced the system engineering, what would be, the possible outcomes? So kind of one, because of system engineering, the power helped NASA do something. And because of lack of system engineering, probably something did not happen or some bad things happen. So that way, based on that can help the general public to get a better understanding of system engineering, why it is important. And if we don't have it, what could be the losses?
Yeah, that's a really good question. It's a very challenging question, actually. Yeah. Stephen Johnson's book, The Secret of Apollo, really, if you want just an easy read book, it really goes into depth of what the difference systems engineering makes in aerospace. That's a really good description of it. And in that book, Stephen talks a little bit about early rocket programs and the large failure rates that you saw with early rocket programs. And I was just in a discussion, we were talking about the aircraft industry, right? So let's take the space shuttle. And that program is retired now. And if you look at the reliability of the space shuttle, it's 98.5%. Okay, so 98.5% of the time we flew the shuttle, it was successful, it landed. Now take passenger aircraft flight and what that means. Passenger aircraft flight is 0.999995 reliable. Okay,
yes.
It's extremely reliable. Would you get on an aircraft that 98% of the time you would arrive safely? You would not. You would not do that as a general public rule because we would be seeing aircraft crashes every day if we were that reliable. And what systems engineering is doing is it's allowing you to figure out how the systems interact so that you can fly safely on a Boeing 777 or an Airbus 320 or any of the other aircraft that you get on as part of your daily lives. And what systems engineering about is understanding those interactions so that we don't have these disastrous failures that you can get on and feel comfortable and safe, as I did yesterday flying here to Cornell from northern Alabama. And it was great, right? I'm not really worrying about that probability because there's a systems engineers have gone through and said, here's the interactions, here's what's important, here's how they work together. When you talk about health management, here's how we deal with the failures. It's not that you don't have failures, it's that we know how to deal with them in a safe and reliable manner. And that's what systems engineering is about, is understanding what makes these very complex systems workable. Practical. How do you take a complex system and put that together and make it work? Because and there's different levels. If your car runs out of gas on the side of a road, you can call somebody and they bring a tank of gas, and we've probably all experienced that at some point in our lives, and fill it back up, and you can get down to the gas station. If an aircraft runs out of fuel, which they do not fly aircraft to allow that to happen. But if you flew one just till the very end and it ran out of fuel, what happens? You coast back and find a safe place to land, right? You can do that. And we've seen aircraft that have had engine losses and they've coasted back and landed safely on roads or in fields. That happens from time to time with small aircraft. And so but that's not as easy as running off and pulling on the side of the road. When you get to a space vehicle and you run out of fuel halfway to the moon, there's a problem, right? How do you get back? Apollo 13 is the one instance where we had a problem and we needed to get the crew back and do that in a safe manner with systems that weren't working correctly and were failing. And they had to deal with it, and we were able to overcome it. It took a lot of really remarkable people in control centers on the ground working with the flight crew that was very diligent and perseverant in the things that they were dealing with, and they were able to return them safely to the ground. A lot of systems engineering involved with that. In fact, we learned from that particular mission, and there are things that we do today to make sure that the problems that they had to overcome are already in place. That's systems engineering. Is how do those systems interactions work, and how do we deal with that, and how do we think about not, we lost the vehicle and we just let it go and crash into the planet or into the ocean or whatever, but we thought about what's going on with the options if that happens. And how do we move that? When we did the vehicle systems management study that I referred to earlier, we said, what happens if halfway to Mars we get struck by a sizable meteorite, which is probably the size of a pea, given the velocities that you're traveling? What if that hits and penetrates and damages the thermal radiator so that we can no longer cool the vehicle like we need to? How do we reorganize that vehicle in the face of that major disaster? How do we reconfigure the systems so that we can maintain the crew's health and get their crew back to Earth safely? It does change our mission objectives now. Mm-hmm. And yet, how do we do that? That's systems engineering, because it's not a question of, well, how do I repair the radiator, which is an option, but it's also, what do I do to reconfigure structural systems to perhaps dissipate more heat? What do I do to change the way I'm working the electrical systems so that the heat dissipation is not as high, right? How do I reoperate the life support system so that I don't create that thermal load? Maybe I change crew activity a little bit. Because believe it or not, if you walk into a room and you think, wow, the room was cool when I got in here, but now there's 100 people in here and it's really hot, it's because human body load is the most generator of thermal heat in the office buildings, right? You can see that when you go into rooms that start cool and get warm. It's because of the number of people in there. Or you walk into an empty room and you stay cold the whole time. It's because the air conditioning was set for a larger heat load. And so how do you deal with that, right? How do you bring all those aspects to play? There are a lot of really intelligent people who can deal with the electronics. And there's a lot of really intelligent people that can deal with the mechanics. And there's a lot of really intelligent people who are dealing with the physiology. And bring all those together into a system and make them work together successfully, reliably, safely, comfortably when you're talking about people traveling. How do you do that? That's systems engineering, bringing about all those together. And that's the next step, right? We've gone about as far as we can, in my opinion, on trying to allow things to kind of grow from the ground up. Sometimes I think of it as brute force engineering. We're putting all the pieces together. We're integrating as best we can. We need to be able to see how to do that in more elegant manners, more intentional. I want it to work this way, and I know how to bring the pieces together so that it does work that way. And do that with less cost, and do that in faster turnaround, so less schedule. And how do we bring that about? That's systems engineering. That's the advancement that we need to make. And that idea of foresight is what systems engineering brings to the table. It's not that it's not just writing good requirements or recognizing interfaces. It's writing good requirements and defining interfaces so that they deal with all the possibilities and they are constructed in a way that those possibilities don't become disasters. And that's what you see in our commercial aircraft today. Those possibilities don't become disasters because they've been engineered out. They don't exist in those systems. And how do you do that with spacecraft, right? That's really what we're trying to go the next step for in systems engineering, is dealing with that. And you know, when you're on the aircraft and you want to use your internet on your phone to talk, right? There's communication issues, bandwidth connections. How do we do that with a crew going to Mars? How do we allow enough communications bandwidth for them to be able to have personal communications, as well as all the science data, as well as all the systems data that we need to talk with, right? So how do you bring those aspects in? And that's the next step. I would love to be able to walk out here to the airport at Ithaca and get on a vehicle that would take me to France and I could have dinner there and then come back, right? We can't do that today, right? It's a 10-hour flight. You know, I get there to France for lunch tomorrow and I can't be at the meetings this afternoon.
Maybe the virtual reality.
Yeah, virtual reality, but I can't have the waiter serve me that wonderful plate of food, right, in Paris, right? It's like, so virtual reality helps a little bit, but helps us to see things and understand things better.
Yes.
But it can't physically transport us there and have that physical experience of that good meal. So how do we? I'd love to see us get there. How do we get there? Well, that's systems engineering. That's taking the next steps. It's taking the next advances. We know how to build the pieces. Can we build the pieces in a way that can allow the general public to be able to safely travel back and forth, as we do with airlines today? And that, to me, is I would love to be able to see that come about. But that's a real systems engineering challenge, and we need to be able to do that in a way that that's elegant, right? Because that's what people really are looking for.
That's right. It's a challenge, and also hopefully it will become a mission.
Yes.
Right. So that's I think, Michael, it's just wonderful because I think you see, you easily pick up all those real projects and you work on, and I think you really kind of told people what system engineering is about and why system engineering is important. And I really you mentioned that system engineering is about making complex systems work.
Yes.
Right, and you work at the interfaces, you work at the the interdependencies and also the interactions. So my question kind of yes, people like me, general audience, we're becoming really interested in system engineering, and it's amazing that at NASA with application of system engineering knowledge and practice, you were able to make those complex systems work, and they were able to transport people, astronauts to the outer space and coming back. So now my next question is how? How can we make complex system work? It's kind of more detailed level because as you mentioned earlier, you mentioned there are many existing NASA processes.
Yes.
And you said that the process can make something work and it could also fail something.
Right.
So which means that system engineering practiced or advanced at NASA is not really a process, right? System engineering is actually probably something bigger and deeper. So now my question is, how can we, of course you've been helping advance system engineering, so how can we consider and cope with emerging behavior in system interactions and interfaces, right? In additional processes, what are other more specific secret source, which will be the DNA of system engineering? So kind of if you can shed light on several aspects, kind of some, because you're now, I think we're gradually getting into the depths of systems engineering, not just as a practice, not like a trial and error. It's really, as you mentioned, advancing system engineering towards a discipline. So what do you see as the key pillars that help us establish and practice system engineering?
Oh, that's a great question. Great question. So there's a lot of different ways to answer that. There's a lot of different aspects to that, right? So we're part of complex systems, and you can find it in the Incosi Complex Systems Primer. You can get that out there at the Incosi bookstore, and you can look at that. Is that complex systems have multi-perspectives, okay? Which means there are different ways to look at them, and when you look at them in those different perspectives, you see very different pieces of the same system, and it's important to understand what those are. So in answer to your question, it's very much a multi-perspective question. One is, you talked about processes, and perhaps the first thing that I would say is processes have a sociological aspect. They're specific to the organization. All right, and what that means is when the processes reflect the organizational structure and the way the organization works, means that the processes are going to be different for different organizations. You see that within NASA, between the different NASA centers. They have different instantiations of the systems engineering processes, and that's good. That's important. We need to have our processes reflect our organization. One of the areas where our processes will start to fail is when they don't reflect the organizational structures and context that we have. And you mentioned several companies, Boeing and Lockheed. You would expect that their systems engineering processes would reflect their corporate values. And in particular, it probably varies between their divisions, aircraft and space. You would expect that to be different. And you see that within NASA, and you'll see that within the automotive industry.
Mm-hmm.
Ford and GM. You would expect it to be different because their organizational culture is different. So when you look at how do we apply the processes, that's what we realized as we were doing the systems engineering principles and understanding that, is that's one of the aspects, is you need to be able to reflect the organizational structure as well as the system. The systems engineering that I do for an automobile is going to look different than what I do for an aircraft. It's going to look different than what I do for a spacecraft. Are there similarities? Yes, but there also are differences. And we need to recognize both and not focus just on one or the other. And so that's an important aspect in guiding the application of systems engineering, is understanding those organizational differences and how that affects the way we apply our systems engineering. It's very important. Another aspect of that is systems engineering modeling, right? And there's been a lot of impact recently on the application of system markup language, SysML. A lot of people refer to that as model-based systems engineering. I think a really important thing to realize about model-based systems engineering is it's model-based systems engineering. Right? It's still systems engineering. The processes still apply. We're just using models to help understand the system so that we can have a better understanding of our systems engineering. So that's really important. But then what is model-based systems engineering? What is contained within that? SysML is a big visible aspect of that right now. A lot of focus in SysML, but that's one of the 6 modeling types that we actually identified in our work in the NASA Systems Engineering Research Consortium. Physics-based models are also important at the system level. And that brings in concepts like thermodynamic exergy, E-X-E-R-G-Y. Mm-hmm. And what we found is that concept, which we actually learned from AFRL Wright-Patterson, is really a integration concept across all of thermodynamics. And so you have exergy. If I'll go into optics, exergy is not the integration concept. It's the optical transfer function, which is a Fourier optics method. And if I go into electrical communication systems or data systems, it's the electrical transfer function. And so you get those different aspects of integration across the different system types. So there's physics-based models, and systems engineers don't have to be experts in the physics, but they do have to understand the physics. And so that's important with these integration models. System state variables are really, really important to understand. I was at a meeting in JPL, and they said, well, there's over 10,000 state variables in our project. And I said, yes, but there's only 200 that are system state variables. So there's a difference. And what are the state variables that cut across and define the system and the interactions of the system? And how do we define that? So there's a couple of models that are out there that have been developed that do that. One's called the goal function tree. It's basically a success tree. It's the logical inverse, and it's mathematically the inverse of the fault trees that people are familiar with. Fault tree analysis. You take the logical inverse of that, you get a success tree. Essentially, you're looking at the goal function tree, which is taking goals of the system, what it's trying to achieve, what are the functions necessary to achieve those goals, and what are the physics state variables that drive those functions so that you know that the function is tangible and not a convolution of other functions, which is really important to be able to sort out and understand. The other is the state analysis model, which is a very powerful modeling technique. You take hardware state models, take software algorithms, you take a system execution timeline, you run that, and you can learn so much about how the system actually behaves and operates. It allows you to do much more testing of system applications and the algorithms than you would be able to do in real-time software testing. Real-time software testing, depending on the system, I might be able to run 100 cases over a couple of years. If I run a state analysis model, I can run 10,000 cases in a day. It's very different. It allows me to really explore the scenario space much more broadly. and understand the system in many more scenarios that I probably don't expect to see happen in actual operation. Yet if they do, I'll know whether my system will be able to operate in those scenarios or not. And if it can't, what's the outcome, right? What do I do with that? And so the system state variable types are very, very powerful. There's system value modeling, which really deals with how do the stakeholders, how do the customers, how do the operators perceive the value of the system. That's just fundamentally important. You can actually create a mathematical structure based on the preferences of these different stakeholders and what they're looking for, and you can actually measure your system success against that. And that gives you a real strong guide of how well you're achieving what the stakeholder actually looked for. And what happens when the stakeholders change or the stakeholder values change, which can happen very quickly. Mm-hmm. What do you do with that, right? Well, value model gives you a measure of that, how things change, and then how you need to adapt to that. And so system value modeling is really important. System statistical modeling is really important to look at understanding systems, their uncertainties, their reliability. All those things are really, really important in systems engineering as well. And that's a pretty standard modeling type that people tend not to think about, but that's something that we've been doing for decades, is system statistical modeling. And there's a lot of statistics out there that are coming back in that people should look at. There's frequentist statistics are pretty standard. We look at the frequencies of occurrence. Mm-hmm. There's Bayesian statistics, but there's also information theoretic statistics that are out there that are, I think, give a better understanding of the system in some ways. Pike information criteria is really important as part of that. And so you can look at those types of aspects of systems engineering. Then there's system dynamics is another important part. And that's something that Erica Palmer here at Cornell really helped me to understand. Is it allows you to look at the social interactions of the system in a very clear manner. Mm-hmm. And deals with stocks and flows. Those stocks can be information or power or thermal, or you can have a lot of different bases. They use a lot in logistics modeling. You can use it for that. But it looks at the buildup of stores of information or physical attributes and the flow that goes through the system. And then you can start to look at the interactions of those stocks and flows, what it's providing out to the stakeholders and what they're giving back and how those interactions play out. So it's a very powerful modeling technique that's not a lot's been done on. It was developed by Jay Forster at MIT back in the late 60s. And I think a very important aspect to systems engineering. That's another modeling type. And then SysML, right? We talked about that. That's a relational model, yes. Right? When you look at SysML and what it's doing, it's allowing you to understand the relationships between the system. Very, very important and an important piece. And that seems to be the entry point into systems modeling within the discipline of systems engineering today. But there's actually a broader scope in that multi-perspective that we need to be looking at. And so these modeling types are really important to help us kind of move forward.
Beautiful. Thank you, Michael. And I think it's kind of apparently, right, system engineering as a discipline, first of all, right, it has to integrate across many existing disciplines, right? So as you were talking about, from, the system dynamics, system statistics, system mechanics, and also system integration, that seems quite a lot.
Yes.
Right, for any average general public, right? Even for you and me, as let's say we went through the PhD training, right? We felt like we were fed more yes. in kind of these approaches. But I think with all these things, for general public, that could feel overwhelming.
Yes.
System engineering, but in the meantime, any discipline, and I think I was really. I'll remember this for the rest of my life. You mentioned this. Actually, I did not know that before. Actually, you mentioned the importance of the theory of material strength. Mm-hmm. That actually kind of created, many, like kind of modern disciplines like civil engineering, mechanical engineering,
Mm-hmm.
right? Looking at these things, right? So somehow you can see that while many disciplinary areas, they seem to be very complicated, but it all in the end boils down to something that could be very simple. And using your word, elegant.
Yes.
Right, very elegant. So how can we make system engineering or system design to be elegant? And I think when I think about elegancy, and I think the way to deal with complexity, especially if you have like a silver bullet
Mm-hmm.
that can deal with any complexity, I think that kind of gets me to very fundamental principles. Because if you have the principles, and if you can follow those principles to deal with any varying scenarios or complexities. So now I really how can we drive engineering or system engineering towards, or design of complex system towards elegance? So and I know that you've been doing research, and actually you've been published on the principles that will guide system engineering. So can you share with us, what are some key guiding principles that will make system engineering elegant?
Oh, sure, sure. I mean, there's 15 principles, and we won't go through all of them here. But the first principle, which really came out of a conversation I had with Michael Griffin, the former NASA administrator, mm-hmm. And former Undersecretary of Defense for Research and Engineering. When we talked about it, I think the way Mike phrased it is systems engineering focus is on the system. Right, not the process, but execution, but the system itself. And I thought, well, that's right. So our first focus is systems engineering is specific to the system, which means I need to understand the physics of that system, whether that's a car or a building or a train or an aircraft or a spacecraft, mm-hmm. Electrical power plant. I need to understand the physics of that system, and I should expect that my systems engineering processes will be affected by that. Right? And then we've also talked about the organizational side, and probably the best principle on that is complex systems are built by complex systems or complex organizations. And actually, if you have two or more people, you and I now form a complex systems, because if you think of all the variations of the way we understand and think about things, and then you add two people together and all the variations in the way that we share and communicate information, becomes very complex. From a cognitive science standpoint, you jump into complexity really fast. And so when you talk about even small companies, let alone large corporations like Boeing or Lockheed, that is a very complex system and a very complex structure. And when we look at large systems, that when we talk about spacecraft, these aren't single company organizations, although we're starting to see that trend now in commercial space. SpaceX is a good example of where a single company is being able to do it. There's still a complex organization. And then when you look at what other companies are doing, where it's not one company but a team of companies across multiple corporations across the world, that's very complex social structures that you're dealing with. Different values, different way to understand things, different way to approach things, what's important, what's not important. All of those things get played in together, and systems engineering has to be able to bring that social structure together to make sure that the information flowing through the organization is being realized in the design. Jennifer Stevens, an engineer at NASA, said to me once, the focus of systems engineering is on the flow of information through the organization. She was right. And so that's something that we really need to focus on as systems engineers, is how is the information flow going through the organization? It's not my job as a systems engineer to manage the organization, but it is my job to figure out how information about the system design is flowing through the organization. Are there gaps where information is not flowing through? that can be a disaster in product realization. Are there barriers, not gaps, but actual barriers to the flow of information? Where are those at? And how do I get the information past those barriers, through those barriers, across those gaps? How do I do that, right? That's a conversation I need to have with the project manager or the organizational manager, but it's still my purview. I can't say, well, the organization was broken, so my system failed. I'm the systems engineer. I need to be able to figure out how to recognize that and how to address that with the right people in the organizational and program management structures. That's a real challenge for systems engineers, and it really brings in aspects of sociology that we're not teaching, but that you'll actually, in a lot of universities, but you'll actually see it underlying some of the processes when you look at how they're actually being implemented. And so that aspect of getting to an elegant system is making sure the information is flowing right through the organization, so it's actually getting into the project, right? If you look at Diane Vaughn's book on the Challenger disaster, right? She kind of illustrates very well how information was known in the organization, but it didn't make it through the decision-making structure, right? And that led to a space disaster. And so how do we make sure that we're connecting all those things, that information is getting properly understood and properly flowing through? That's a real challenge for systems engineers and something that we need to focus more on. If you're intuitive to systems engineering, you probably recognize that. You're probably already doing that. If it's not intuitive to you, it's something you can learn. And it's something that you should be able to recognize and study and understand. And so I think that's an important part of systems engineering that allows us to get to elegant systems. Understanding the system completely is really important. One of the principles, sub-principle actually, is requirements are a reflection of the understanding of the system as engineered. Mm-hmm. They are not a reflection of the system itself. They only reflect how well the systems engineer knew to put it down. We need to recognize that, because our understanding will mature as we go through the system development process. It's something that one of our best systems engineers from the Apollo program, from the Saturn program specifically, Bob Ryan told me. He said, our engineering understanding evolves as we go through the design and development. There are things that we learn about the system as we get into tests that we didn't know when we wrote the requirements. We would have written the requirements different, right? So then how do we deal with that evolving understanding? We need to recognize that and capture that as part of our process flows. Requirements definition is still important, but reflecting the evolving nature, we've always tried to say, maybe we should design that out. We just need to know it better up front. Bob's point was, no, you will never know it better up front. You have to go through the development process to understand it. And that gets us back to elegant systems. Planning for that, allowing for that, knowing how to deal with that appropriately, right? Not being surprised by learning something new, but expecting that to happen, right? That informs our requirements so that we write our requirements better. That gets us more to an elegant solution as we go through things. If you look at the history of elegant solutions, a lot of those coming out of very extensive test programs and knowledge that people have, learning from that and what they're doing. And so you can see that in some of the commercial space aspects, right, where they're doing a lot of testing and learning. That's really important to an organizational understanding. That contributes to the elegant system, because you don't want to field something and have it fail. And then you spent a lot of money for something that didn't work. Right? That's not what we want. To get to those elegant solutions means we have to have a better understanding. Have a better understanding means maybe I didn't take a crate and put wheels on it and call it a car. Maybe I did something that has a very stylish design to it. You know, that aspect of style is important as part of the elegant solution. And I can't prove this, and I won't tell you that it's an absolute, maybe it's a heuristic more than a principle, is that style is reflected, or the physics are reflected in the style. Those are connected. I don't think we really understand today how they are connected, right? But that's an aspect of art that plays into the engineering. And so how does that work out? I believe that elegant solutions, when they properly meet the physics, they also properly have an artistic flow to them, a symmetry to them that we see and understand in some aspects. And sometimes asymmetry is asymmetry, right? And so how does that come about, right? And understanding that's a whole area that I think would be really interesting to look at if we can make those connections. But that's kind of getting back towards your elegant side too.
So Michael, as we said, system engineering is still an emergent disciplinary area, and we need people like you. I think you are really a treasure, not only knowing where we are, but also knowing where we were and how we got here today.
Yes.
It's really like a kind of any new area. It's like kind of people in the frontier you were exploring in the darkness. And at some point you're excited, oh, I discovered this light. That's the right direction. So when you see that light, of course, you keep moving things forward. But in the meantime, I feel you probably feel the propelling excitement that you want to let more people to join you, in this exploration and this advancement. Actually, I think, given our time, I will come to our last, question. It's really about education, right? You can see that it was not easy, right? It was not easy. All the experience, all the knowledge you gained from previous success as well as the failures you observed, right, from this. And how can we make sure that all this knowledge and also this appreciation of system engineering can be passed along to our future generations so that they can continue the course, right? So, of course, Cornell System Engineering, as I briefly introduced you earlier, actually, we are on a very good foundation now. We run a full spectrum of the graduate degree programs. We don't have undergraduate, and you know why? Because for system engineering, we feel strongly that we want to establish that T-shaped knowledge structure, right? With people, they do have some solid training in certain discipline areas, and then when they get to certain state of their career, and then they can be equipped with this horizontal bar, which you probably picked up through your whole career, right? So system engineering education, and especially here Cornell System Engineering program, we are aiming to build a top system engineering education, graduate level education program. So with all your knowledge and all your experience, expertise, what do you think we should have in our system engineering curriculum, such that it will kind of help advance and also achieve some of the goals that you have in mind for our future system engineering advancement? Yeah.
So Mike Griffin and I actually had a conversation on this back, 2012 maybe, about what would be a curriculum for systems engineering. And what we came up with was is you need a broad understanding, right? So you don't need to go in depth in anything, but I need to know Maxwell's laws. I need to know the basics of statistics, dynamics, and thermodynamics. I need to know the basics of computer architecture and software engineering, right? How the software works, how it's coded, how it's integrated. I need to have all those. So if you think about a systems engineering curriculum, what we talked about was having systems engineering cover all the intro level classes of all the engineering disciplines at a school. And so you get that broad understanding. And then go beyond that with some of the things that I've talked about here. Category theory, I think, is important to bring in. Nobody's really teaching category theory outside of mathematics, and there's not a lot of colleges I'm aware of that are teaching category theory as part of their math departments either. So that's an important piece of it. I also think you would add, we talked a lot about adding capstones classes. I think that's really important to have a capstone course, whether it's undergraduate or graduate. I also believe that when looking at, like I said, first principle systems engineering is specific to the system. So what kind of emphasis area do your students want to have? Mm-hmm. If your students want to have an understanding of nuclear power plants, then there's going to need to be some nuclear physics courses in there to understand how the reactors work. If your students want to have an aircraft focus, then they're going to need some understanding of aerodynamics, right? Yeah. And so that may not be every systems engineer, but those that want to work in aircraft need to have that. If you want to work in the automotive industry, you're going to need to know the difference between the Otto cycle and the diesel cycle and what that means and what is transmissions and all that. A lot of that's covered in mechanical engineering, but those specific are thermodynamics, but those specifics probably need to be built on a little bit more for the automotive students, right? And so these become elective courses is the way Mike and I talked about it. Or if you're going to go to spacecraft, orbital mechanics is really important, right? But not every systems engineer would need to know that if they don't plan to work in aerospace. Yeah. So that's kind of the way that we structured what we talked about. I think that's a good template. You could look at undergraduate in that sense. If you have somebody coming into graduate school, as I did, I'm electrical engineering all the way through, then they have that electrical engineering basis, but then do they have the other aspects, right, and how to broaden that out, right? So I do believe that if you can accomplish that, if schools can accomplish that we could graduate systems engineers who are effective at systems engineering day one. There's a theory out there that you need to have 20 years experience in something before you can actually be a good systems engineer. And I was a systems engineer 3 months after I hired into NASA. And successfully took my programs through their reviews. So I believe that we can, if we have the right academic structure, as I've discussed, produce systems engineers who are effective day one. And a lot of times I've talked about it, there are really intuitive engineers who are good regardless of the education they have. There are really good electrical engineers that are designing our latest processors at Intel and AMD and other companies out there. But we're also graduating 1 million electrical engineers who are just really good at doing electrical engineering, right? Mm-hmm. So you don't have to be intuitively great to be a great electrical engineer or a mechanical engineer or a civil engineer. Mm-hmm. It's the same thing as systems engineering. Right now we're kind of depending on experience in another discipline, and those that are really intuitively good at will be successful at systems engineering. What we need to get to is being able to develop and have systems engineers who are really successful, who it may not be intuitive to them, but it is very interesting and something that they would like to pursue. Then I think they ought to have the opportunity to do that. And I don't think they should have to work 20 years in another engineering discipline before they start. Mm-hmm. And so I think we can do that. I think that the construct that Mike and I talked about really kind of lays that out and gives you that jumping off point to be effective. And I think that's a good direction for us to go in systems engineering.
That's great. Thank you, Michael. I think this is a good point for, I know that you have your Ezra seminar talk coming up in about 10 minutes. So I don't want to hold us up for too long. But this is great. I think this is a good point for us to stop. And especially, I can feel the, optimism that you have for system engineer. And I think Cornell System Engineering Pro will definitely make our effort to make that into reality. So I think I'll talk to. I think we're done.
Okay.
So we're done. I think that was great. Thank you, Michael.
Thank you.
I think this is really, to me, the most comprehensive discussion that I have had about system engineering. Especially you kind of embedded all those things in the history of NASA, so many NASA projects, and those are the real instruction cases, right? I think that's wonderful.